Welcome to ECE 441A, 541A. We are starting the fall semester, and I think that sound is vehicles driving on top of us if you're in the classroom. If you're at home in a closet or wherever you're watching these videos, you can just pretend that you're hearing something running across your ceiling. Sounds like animals maybe playing above us, but I think those are maybe vehicles. I don't know, it kind of bothers me, but I'll try to tune it out. Obviously, I'm not doing that, am I, right now? I'll start class typically with some announcements, and then we'll go through the goals, and then we'll get right into the material. The first announcement is a passport assignment. That's your passport into the class, and that should be available on D2L, which is d2l.arizona.edu, and that's due in 7 days, in about a week. There's also a prerequisite quiz exam on D2L that everyone, online and on-campus students, need to complete. I'm not sure of the date. I put the date on there Saturday, and yesterday I forgot what date it was. So that 5 of September may be flexible, but try to get it done as soon as you can relative to the start of the semester, and that's to give you a sense, or give me a sense, of where you're coming from. If you don't know the answer, that's fine, that's okay. We'll just figure out what needs to be done relative to the semester. And if you're already filling out your calendar for the semester, homework number 1 is due on the 10th of September. It's not yet available, but I'm wanting you to put that in your calendar so that you know that you do have an assignment coming at you that's due on the 10th of September. If you didn't know, since I'm wearing 2 microphones, we're recording this. I'm trying to make this available to the online class, and so these notes and the on-campus students should have access to that same information. So if you miss something in class, or you want to rewind it for whatever reason, maybe something wasn't quite clear, you can go back and find that and play it again for hopefully you to make more sense out of the discussion. The syllabus, actually, maybe I should give you some clues. Here's the passport assignment. The passport assignment is your name, and please provide a pronunciation guide. Not that I am the best at even following your guide, but it does help me at least struggle through. I want to get your name right. Photograph, that should be a fairly recent photograph. Maybe not a 2-year-old picture of you. I might not be able to do the age progression accurately, but something that I can sort of look around and say, oh, yes, I've seen their passport. And the third question on that passport is, what would be a tip that you would provide to another electrical and computer engineering student that's coming up behind you, that you could say, oh, this is what I would recommend or suggest for success in that ECE curriculum, in the ECE curriculum. You've made it already to what? Your senior year, probably. This is a technical elective if you're in 441A. You may be first semester students at the graduate level. Then you're in 541A. So some of you are finishing your careers, some of you are starting your careers, but we're mixed in here. But the ones that are starting have already received 1 degree. So don't feel too uncomfortable. You should have the material that you need, or the knowledge and skills you need to succeed. Yes? There should be plenty of sheets passing around, so if you're not supposed to be on the 540, the question was, and that's what I need to try to remember, is to repeat questions, because you probably won't get picked up by the microphone, although I'm wearing about a zillion of these microphones, recording devices. But you should be able to find the page that pertains to your class, and it may come around to you. If you can't, if it's 947 and you're nervous, sign the other one and put your particular section on it. That's fine. I just sort of want to see who's here, who's absent, etc. The next to the last part of the passport is you to have read the syllabus. And for me to, you don't need to necessarily sign that. As long as you put it in the drop box, that's your signature to me. That's your verification that you're agreeing to all the details of this contract or passport. The fourth part of the passport is to write 2 different sets of sentences, one on good study habits and the second on bad study habits. I'm giving you a link to those. You can read those and identify with or select from those 2 sets what sort of talks to you right now in terms of, oh, I'm going to use that one. That one sounds really good. Oh, I want to make sure and avoid that one. Probably one of those bad ones is no sleep. Sleep is so important, and we're finally, that's becoming communicated to the masses, I hope, that a good night's sleep is probably more important than trying to cram for the exam. So if you're planning the exam, plan far enough in advance so that you can study prior to the night before, so that you're not up all day and you come in here the day of the exam and you fall asleep or mentally fall asleep. Question? So the last semester assignment, did I have the 10 rules of bad? I did. I was trying to remember which one. All right, maybe I'll come up with a different one. So stay tuned. How's that? You have a few days. I thought I went back and checked. Oh, well, Saturday was hastily disappearing, so obviously maybe I put the wrong piece in the wrong passport. So the question was, I just did this last semester. Well, then do it again, is the answer. No. So I'll see if I can get something different. I know the tip for success wasn't on that last semester's passport. So double check. They start running together, but I thought that I did my homework, but maybe not. If you didn't know, I'm Hal Tharp. This is, now we're talking about the syllabus. And the office hours are listed. There's some justification for why you might want to take this class, tips for success, and then there's textbooks. How many, show of hands? So we're in a collaborative learning space. We're going to try to take advantage of this. You have the ability to maybe write more, so you should be bringing material in that you can write on and maybe turn in to me as we go through the semester. I may make that as discussion posts for the online students. They may have more asynchronous interaction, but at least they'll have some interaction with their fellow students. How many, show of hands, have purchased the, which edition are we on? I didn't even list it. 13th edition of Dorf Bishop. Not very many. So it's only, what, $250 at the bookstore? Oh, I went and looked. So we will be using that book, but I also have provided other resources that are available to you either through the web or through the U of A library as ebooks or soft copy versions. And you can, I hope, get some of the information, most of the information, maybe from these other reference sources if you didn't purchase the book, or you can share the book. And the book is nice because it has MATLAB sections, That's where we will draw our homework problems from, but we'll figure out a strategy for that as well. This is the normal material that I'm supposed to include in a syllabus. Don't get dizzy watching it. Exams, we're going to have 3 exams and a final. We'll have probably 10 homeworks, and here's the tentative dates on those exams if you're blocking out your calendar. The 21st of September, somebody has already given me interesting look, so I'm curious what conflicts already exist with respect to these exam dates, and we can talk about that offline. But these are the planned days. The final exam, I believe December 11th, is actually a Tuesday. So if you're only on campus Monday, Wednesday, and Friday, starting the finals week, you're going to have to readjust your schedule. And that one is from 10:30 to 12:30 in the morning, so you can sleep in a little longer, but it's a Tuesday and not a Monday, Wednesday, Friday. We will have labs. These will be on your own in terms of going into the laboratory and executing the lab instructions. But most of it, once you've gone in and shaken the system, I say shake, it's a mechanical system, and you'll actually be moving it around with commands. Once you've done that, you can actually put the data that you've collected on a flash drive and go home. The equipment is a little bit dated in the lab, so be patient, but at least you can collect the data. You can go home and analyze it on your own somewhere else or with other resources. But we will have 3 different labs, and it will follow us through the semester. The first one is, how do you identify a system with data? How do you push it around and then extract the model from that? And then how do you make that system? I'm going to probably trip and fall sometime this semester. Just sort of humor me, laugh, or whatever feels comfortable for you. Hopefully I won't be hurt. If I am, that's okay. You can just leave. Take advantage of the sick day or the... Anyway, we'll make do. The other one is, how do you change the dynamic behavior? And finally, how do you change the dynamic behavior via a controller design? Those are our 3 labs that we will have. And here's probably the one section of the syllabus you're really interested in, the class cancellations. Labor Day, there's an engineer's breakfast that occurs from 8 to 10, and so I'm going to give you that time off to enjoy a breakfast with your fellow peers or alums, if that's possible. Veterans Day is on a Monday, and Thanksgiving recess, one of the Fridays on that recess, will impact us. You won't be needing to come to class there. This is the final exam right here, so we'll skip over that. But again, this is all on the D2L website, but that's the list of topics that if you can do those, maybe forwards and backwards, you should be okay for the final. With this outline, the way that you can use this is to read ahead. I'm expecting you to sort of read in advance. If I now give you an assignment in class and you're working on it in class, maybe it won't make any sense at all if you haven't pre-read the material or maybe even watched a video. I might give you some pre-class videos that you can watch. They're helpful if you need to fall asleep. But and that might prepare you, I hope, for the class the following day or the days to come. But the way that you can use this outline is to look at the topics and correlate that with the references that you're using. If you're not using the textbook, you can now start to see, oh, does this book have something to do with modeling, mechanical system modeling, electrical circuit modeling, or electromechanical, Bode diagrams, or state space representation? How do we do that? Well, all of this is now explained or lined up relative to our homework assignments and our exams, and you can hopefully clue yourself in as to the topics that we're covering when and how we're covering the material in the course. Are there questions about the syllabus? And if I don't see your hand, you can shout at me or try to get my attention. Maybe not shout, but Dr. Thorne. Anyway, I'll try to hear you if possible. We've now gone over the syllabus. The first thing that I'm going to do is actually have you do an activity, which is to model an electric circuit. Then we'll do the course overview and we'll have some wrap-up questions. Here's your chance to show me how much you remember from the summer break, and that is to develop a model for this electric circuit. Go. You have a few minutes, and you can work amongst yourselves if that feels better for you. You can work individually, you can work with your team, but now I'm going to give you 3 or 4 minutes to come up with a model of this electric circuit.
We were watching your eyes drift and it like hit half and then you hit over there.
So, yeah, we were just wondering if we could get some clarification. So, when we think about this kind of problem in past courses, we always have kind of like a defined output. And we're modeling in terms of the input and the output.
So the question was, you're not giving us much information, and that's intentional. The question was, I'm looking for an input and an output. What are you doing? So now that's what I'm wanting you to start thinking about, trying to figure out, what do I need? If your boss threw you in a room and said, fix this, you're going, uh-oh, now what? How do I start? What needs to happen? So, some of those kinds of questions I'm leaving them open for now for you to decide. And the idea behind this is to try to get you motivated to follow along when I start maybe deriving equations that govern dynamic relationships for circuits. You're going to say, oh, that's what I forgot to do. Oh, yes. It'll make maybe it a little more motivating, the material. 1 minute left.
Oh, yeah, no, man. It's
All right, now that I've completely frustrated you, maybe not, I don't know that I'm going to even answer the question yet. But that's now trying to motivate you in terms of your reading. What do I need to know in this class? There's prerequisite material on the website. You can go back and start learning about. But one of the first things you might be interested in is what output do I need? Is it the current? Is it the voltage across one of these devices? That's how many people tried to derive a transfer function or went in the frequency domain with S domain variables? Few of you. How many did state space? That's okay. We'll get to state space representations, and they're both useful for different reasons. And that's, I hope, something that you can now think about when you're starting to read and work through, and maybe in the next lecture or two, we'll start analyzing electrical circuits, and you'll say, okay, now I know, now I can figure this out, now I can find a transfer function, now I can find a state space representation. That's my model. That is a model, not the model. But did I say a? I think I did. Develop a model. There's many different ways of modeling that circuit. And that's actually the first part of the class. The class is really separated into three different pieces or parts. The first part is modeling, so that's where we're going to begin this class. We'll then transition into how do we analyze these systems? Are they giving us the behavior, the performance that we want? And if not, that's the reason we go into the third part, which is how do we design controllers to manipulate the system dynamics to make it behave more effectively or in the way that we want it to behave. In this class, then, we are going to spend some time with modeling in the continuous time setting, and there's two main, well, we are going to really be saying, let's look at modeling these via physics. For example, in a mechanical system, what's the equation that you'll just recite? And I cued you in with the F. F equals ma, right? So with a mechanical system, you might be using F equal ma to develop the equations, and I'll say this many different ways, but the governing dynamics, the way this system behaves, its model, there's many different ways of referring to this, but that's now how we might treat a mechanical system. For electrical systems, do you remember Eli the Iceman? And if you don't, you need to get comfortable with Eli and ice, but there is a mnemonic to try to remind us the differential relationships of voltage and current associated with an inductor and a capacitor. And here we're using electromotive for voltage. That's where the E comes from, because it's kind of hard to find names that start with V, Vli, or whatever. But this is Eli. Here's E, L, and I. And then here is I, C, and E, where the first variable is the variable on the left of the equality, and the next two variables to tell us, one, the parameter that we're interested in, inductors or capacitors, and the second one is the derivative of that particular variable, current or voltage. There is then how we will start to be thinking about electrical systems. We also are going to worry about interconnecting electrical and mechanical into electromechanical systems, motors, that now, and generators. Those are devices that connect mechanical variables with electrical variables. Maybe you apply a voltage and that now allows that motor to start spinning, a mechanical action. So electromechanical, those are sort of the key ones that we will deal with in this class. The second way that we will learn how to model systems is via system identification. With system identification, you're going to go into the lab and you're going to kick the system, not literally, but you're going to push it with some input commands. And the system might now do something like that. This is now a time domain, and this might be the output. That might be the position of the mass in our mechanical system in the lab. And based on that, we can now identify eventually where we might end up. Let's say there's our steady state value. We might have a peak value that we can measure. We might measure the time that that peaks, the time to peak. This distance here we will call the overshoot, and we can then compare that with where we end up, y steady state, to actually find the percent overshoot. We also might want to know, theoretically, we never really settle in a linear system. It just keeps bouncing back and forth, but eventually we will get inside a tube. And that tube could be a 2% tube. It could be, and that's what I'm trying to indicate with the dashed lines here. If I say, what's the 2% settling time? That's now the time, the first time that that response enters into that 2% tube and stays inside that tube. You can see that if I move that 2% tube further to the left, I'm going in and out of that tube a few times, but eventually I will go inside that tube and never exit. That will be my settling time, and we could have that referred to as, let's say, T sub s. So here was our peak time, and here is our settling time. And depending on who's asking, we may have a 2% settling time, a 1% settling time. We can talk about those and what that means relative to the time interval, capital T sub s. But all of those are now going to be used to allow us to indirectly find a transfer function for our system. And that's our first lab. We know how this mass spring damper system might physically be modeled, but now we want to measure some data and actually extract or then infer the transfer function from that data without going in and physically trying to determine the spring constant, the damping, the mass. Maybe I'll tell you what the masses are, and that will help you determine some of that transfer function. You could also excite that system with a bunch of frequencies, sinusoids, and examine how the system now behaves at those particular frequencies. And that would then be a frequency domain identification process. And it might now give you something like that. And what do we call that? A Bode plot. Here's now, let's say, the magnitude in dB of our transfer function relative to some frequency. Now we have a Bode plot. And what do those slope changes indicate to us? What can we extract from the system based on those slope changes? Pardon? So now this gives us information about different singularities in the system, either zeros or poles. In this particular diagram, what do these slope changes correspond to? Here, let's say here's omega 1, I'm sorry, omega 0, omega 1. In this particular diagram, what is happening, or what singularity, 0 or pole, is happening at omega 1 and omega 0? Those are poles because we're going down. We now know that we have poles at these frequencies, omega 0 and omega 1. That's the first part of the class. How do we start measuring or modeling system dynamics? Once we have a model, now we can go into the second piece of the class, which is analysis. And like we did for some of the modeling, we can do this in the time domain, and we can also do it in the frequency domain. If we do it in the time domain, now we might be looking at differential equations and similar behavior that we've already looked at in the modeling. We might have some time response, and from that time response we're going to figure out what is my peak time, settling time, etc. Which settling time am I wanting? What's my percent overshoot? So we have all of these that maybe we're not happy with, and for that reason we might now want to know, oh, my boss actually wants the percent overshoot to be 10% and not 80%. Oh, well, I'm glad I analyzed the problem. Now I can figure out what I need to do to hopefully allow me to meet the design specifications that are being requested. In the frequency domain of analysis, instead of differential equations, now we may be having transfer functions. Now we have this S variable that everybody kind of likes. They get very warm and fuzzy when you start throwing S's around. Because what does that do to these differential equations that maybe you like or prefer in the frequency domain? What do the S's do when you work in the frequency domain? The math is easier, isn't it? Now we're doing sort of algebra instead of solving differential equations. We've already looked at Bode plots. Another plot that we will look at in this class is a pole zero diagram, or the S-plane, where this is now a complex plane. Here's imaginary values, here's real values, and we might now place on this complex plane where our poles are located. We might have a pole there, we might have a pole there, and if we have real coefficients in our system, those complex poles have to occur in complex conjugate pairs. But now somebody might say, well, I want to control this system, and they put it into a closed loop configuration and they start adjusting the gain. Now those poles actually are changing from open loop poles, which are the X's, to closed loop poles, and you'll learn how to sketch a root locus based on this kind of system description of poles and zeros and adjusting parameters in that diagram or in that system model. And typically in this class, in the analog class, the automatic control class, the place we usually try to avoid is the right half plane. The right half plane now has positive values of exponents, and that now goes unbounded if you cranked up the gain and said, oh, your closed loop poles are now at those locations. Even though we have one that's stable, we have two that are unstable, and that causes our whole system to behave in an unacceptable manner. It now goes unbounded in a very short amount of time. So we'll learn how to sketch those root locus diagrams in this class. The third part of the class is going to be talking about controller design. And we'll have to get familiar in the first part of the class with block diagrams. If this is now our plant, or maybe you feel more comfortable calling it a system. Remember the RLC circuit that we started with in this class. You could say, oh, that's now in this box. And now I want to control possibly the current in that circuit. And you're now wanting to change the dynamic behavior of that system, and you're going to do it by introducing a measurement of the output, Y of S, and feeding that back and comparing that with some reference input command, R of S, and feeding that information through another set of dynamics, another transfer function, which we're calling D of S, to produce an input to the plant, U of S, that's in this closed loop configuration. What we are going to try to better understand in this class is how do we create these D of S's. How is that done? And we have tools now built up from the first two parts of the class. We can look at designing controllers based on a root locus diagram or reshaping that. Maybe we want to reform a Bode plot, make it bend and kink in different places. How do we do that? How do we make those adjustments in the frequency domain by pole and zero selection in our controller? Or how do we do this using state space approaches? We're going to grow or do this gradually. The first controllers that we will probably deal with will be D of S's that are actually first order. By first order, that means we have a first order or a denominator expression in D of S that has S to the first power. That's first order. And we can build these or figure out how do we pick S and P and K by the choice or using our analysis tools of root locus and Bode plots. How do we start adjusting or figuring out how to select Z, P, and K? In state space design, now we're doing, and this is actually what we will do in the second lab, is we will actually do full state feedback. In the lab, we will assume that we can measure the position and velocity of this mechanical system. And then we'll feed those signals back after adjusting them with gains and putting those back in to drive our system to hopefully make that original mass spring damper system behave differently. For example, well, before I do, let me just go ahead. So now what you may have, when you hit that system initially and just let it shake, it may look like that. After you've designed a controller, maybe it looks more like that. Very little overshoot, and it gets to a final value more quickly. This is now the controlled response. And the blue curve is our open loop response. And what I haven't done up here yet is say that we can actually do more than first order controllers. We can get higher order. We can put more poles and zeros into our controllers. One of those strategies, and for those of you that have already had 442 or 542, you know how to refer to this. What is this kind of a controller? It's not a PID, is it? It's a PID. So now we have a proportional integral derivative controller that turns out to be essentially second order, and we can figure out how to sprinkle those poles and zeros via either root locus strategies or Bode Plot or frequency domain strategies. And with full state feedback, maybe we can't physically go in and measure all the positions and velocities, temperatures, currents, voltages of our complicated system. Maybe we have to build up an observer that will actually recreate those variables and then use that to control our system. Within the full state feedback strategy, with time, we'll figure out how do we, well, it's not really from full state. We're going now from the state space down into an observer and using those observer variables to now figure out what we want to accomplish with our controller design. That's, in a nutshell, an overview of the class. Those are the three parts of the class. We have modeling, which you now are experts in modeling. You demonstrated that with your model for the electrical circuit, correct? Yeah, okay. Very, very confident looks coming back from the audience. And if you're playing along at home, you can look into the mirror and give a confident look to that response or that answer to the question. We'll figure out how to analyze systems and then how to build controllers. With that said, what I would like to do is actually give you a little bit of a time to provide me with answers to the following two questions. These are the wrap-up questions. What are you looking forward to learning or doing in this class? That's question one. And question two is, what have you heard about this class that concerns you? Or if you haven't heard anything after the overview, what concerns you? And so you might just say, I didn't ever hear anything, but this is what's concerning me. If you've actually heard something through gossip, I'm sure a few of you talk to each other and maybe to others. What are you concerned about? And what are you looking forward to? So spend the rest of the time, which is 5 minutes, answering those two questions. Are there questions on those questions? I think they're clear. Are there questions about anything else in the class before I disconnect?